Welcome back. So as quickly as we started this HL topic, we're going to finish it. This is a really small one. So this is the second type of calculation that we're going to do. We'll do a couple of worked examples, and this is basically looking at an application of electrolysis. Okay, so we're going to be looking at Faraday's laws specifically and how to do calculations, but we'll also talk about how we use those for application. So let's have a quick look at our learning objectives. We need to be able to describe an electrolytic cell and the products formed during the electrolysis of various aqueous solutions, which we have already covered, and hopefully you've watched that video. Okay, we need to understand that there can be competition at the electrode, which is something that we're just kind of adding in a little bit more here for HL, and that competition depends on the electrolyte, the electrodes, and the other situations in our cell. We need to understand that the amount of product produced by discharge in an electrode is related to the amount of charge in coulombs that has been passed through the cell. So basically this is just introducing this constant to us, that 1 mole of electrons produces 1 Faraday of charge, and 1 Faraday of charge is 96,500 coulombs, and that is in your data booklet. We need to understand that cells in series, the amount of metal deposited at the cathode in the different cells will be in a simple whole number ratio that corresponds to the charges on the metal ions involved. We'll get to that. And we need to understand that electroplating is an application of electrolysis. So essentially, if you ever think, if you've ever worn silver-plated jewelry or gold-plated jewelry, you've seen a chrome-plated bumper bar on a classic car, all that stuff is done through electroplating. So where we refer to plating, it's electroplating we're talking about. Okay, so this is how we set up for electroplating. Essentially, we have an electrolytic cell. So remember, there's no separation between the different half cells for an electrolytic cell because it's a non-spontaneous reaction. So we don't have to worry about the reactants being in the same vessel because they won't react until we turn on the power supply. So essentially when we electroplate, we deposit a layer of metal on the surface of another metal by electrolysis. If you remember when reduction occurs at the cathode in a voltaic cell, we get a buildup of the metal that is being deposited onto the cathode, so it gets larger over time. And essentially we're using that idea to put a coating of a metal onto another metal object, but this time it's a non-spontaneous reaction. So we can do this with things like gold and other things like that in order to create a thin layer on perhaps a cheaper metal. So the cathode is always the object that you want to plate. So in this example here we have a tin can because this is used for actually plating steel cans which easily corrode with a layer of something else that doesn't corrode as easily and contaminate the food. So we need an electrode of the metal that we want to plate onto our object at the anode. So if you think about this one is going to oxidize and donate, in this case it's tin, so it's going to donate tin into the electrolyte. The tin ions are going to travel across towards our cathode, which in an electrolytic cell is negative, and then they're going to be deposited onto this metal object that forms our cathode. So the key thing is the anode has to be the metal that we want to plate. The electrolyte solution must have the ion or be a salt of the metal that we want to plate. And then at the cathode, we have to have the item that we want to plate. And of course, it's electrolysis, so we have to have a power supply. The cathode is connected to the negative terminal of the power supply, and the anode is connected to the positive terminal of the power supply. So what's happening here is that the power supply acts as an electron pump. It's pushing electrons down into the cathode, okay, which is now a negative electrode, and then sucks the electrons up, removes the electrons from the positive electrode as they're generated by the oxidation reaction. So this is just a bit of a close-up of it. So as this is still a redox reaction, so we can't have oxidation without reduction. So as the tin is oxidized off the anode, then it is deposited by being reduced onto our cathode, in this case the object. You can notice here that our two half equations actually end up being Sn2 plus 2 electrons goes to Sn solid, at our cathode, and at the anode, Sn solid is going to Sn2 plus 2 electrons. So overall, the electrolyte solution, the concentration of tin isn't going to change at all, because we're oxidizing new tin ions into the solution at the same time we're reducing them on the other side. Okay, so there's actually no overall change in tin concentration as this cell is running. So Faraday's laws basically give us a way to quantify this process, because if we're doing electroplating in industry, we essentially want to know how much metal is being plated for the amount of charge, or how long we need to leave something running on the electric current to get the product that we want. Okay, so we use Faraday's laws of electrolysis to pretty much help us work this out. Okay, some terms and some new symbols and some new constants. We've already defined EMF, we've defined cell potential. When we talk about cells in series, we're talking these cells being connected along the same path so that when the current flows, it has to flow in and out of each cell as it goes. Okay, of course, we all know time is given the symbol T, and in this case, the unit is in seconds. So when we use these equations, we must make sure that our time is in seconds. Current is what we measure in amps, and in one of those crazy symbol doesn't match the name, the symbol it gets is capital I. Okay, electric charge is given capital Q, which is and the unit of coulombs, and then we end up with this equation where we can work out the amount of electric charge that passes through a cell if we know the current that is being applied and the time that it is being applied for. So we can use an ammeter to measure our current. We can therefore know the amount of current, and we can multiply it by the amount of time that it's applied for. The other thing we need to define is 1 Faraday. And the Faraday is simply defined as the charge on 1 mole of electrons. It's given the symbol F, and therefore it's given the units of coulombs per mole. And this appears in your data booklet. 1 Faraday is equal to 96,500 coulombs per mole. So if you haven't figured this out already, that means we're heading to a new equation for the mole, where the number of mole of substance can be given by dividing the charge that goes through a cell by Faraday. Okay, or N is equal to IT over F. Okay, so a couple more equations for the mole heading our way. So if we look at this in terms of Faraday's first law, okay, Faraday's first law says that the mass of metal produced at the cathode is directly proportional to the quantity of electrical charge passed through the cell. Kind of makes sense. As we pass charge through the cell, we're pushing electrons in so reduction can occur. In this case, in this electron, we're actually looking at silver, and if you think silver is Ag+, so for every electron that is pushed through the cell, we will see 1 silver atom being reduced. So it's always a 1:1 ratio. Okay, so if this experiment is performed in different cells under different conditions, the same graph is obtained as long as silver is the only product at the cathode. Okay, so mass is proportional to the amount of charge that goes through it. Now, if we look at this one, though, when we do the same experiment with other metals, we see the same trend, but our gradients differ. So if this is silver here, we can see that lead has a slightly lower gradient, tin has a lower gradient, copper and chromium. Okay, and this is for mass of metal deposited at the electrode. So when we plot the relationship between mass and charge for different metals, it follows that the first law follows the first law, but there's a little relationship between the different metals because they all have different masses, so they're all linear, but there doesn't seem to be a relationship between the different metals. Of course, we're chemists, so why are we talking about mass? If we talk about the amount of metal deposited in a mole, things become a lot clearer in terms of the way that we think. If I want to deposit 1 mole of silver ions, then I need to put through 1 mole of electrons, 96,500 coulombs, 1 mole. Okay, If I go then and look at copper, tin and lead, and if you remember your common ions of these, they're all 2+. And if we have a look, the amount of coulombs that we need to deposit 1 mole of copper, tin or lead is actually 193,000, which is 2 Faraday of charge. So in order to deposit a 1 mole of metal with a 2+ charge, I have to put in 2 mole of electrons. Makes sense. And then chromium, good old Cr3+. If I want to deposit 1 mole of chromium and make a nice chrome bumper, I need to put through 3 mole of charge because I need 3 mole of electrons to account for that 3+ charge. If you remember, Cr3+ plus 3 electrons gives me Cr solid. Okay, so now we can see these half equations are critical because I need to be able to work out the stoichiometric ratio between my electrons and the metal I want to plate. So if Q is equal to IT, and then we have the next one, Q is equal to the n of electrons times F. We've already talked about this. We have a new equation for the number of mole. In order to use Faraday's laws, I need to be able to know the current that goes through the charge, how long for. There I'll get Q equals IT. Then that will give me the charge. I divide the charge by 1 Faraday, and that gives me the number of mole of electrons that have passed through. I use the mole ratio in the equation between the number of mole of metal and the electrons, and then I can work out the mass of metal that will be deposited on the item at the cathode. Let's have a look at it. So we're taking a silver plating cell, so when we look at these, we need to think carefully about what is the metal that I'm plating, and then what can we do from there. So in this case, we have a silver plating cell. It operates with a steady current, so the current isn't changing. So I is equal to 30 amps, okay, for 20 minutes. Catch, time has to be in seconds. So time is going to be equal to 20 multiplied, of course, there are 60 seconds in every minute. Okay, so when I get so Q is equal to IT, so it's going to be equal to 30 multiplied by 20 multiplied by 60, which is going to give me 3,600 coulombs going through our cell. Okay, so now I need to work out the mass of silver. So if this is my 36,000, get an extra 0 in there. If this is my number of coulombs, now I need to find out my number of mole. So if my number of mole of electrons is going to be equal to Q divided by Faraday, remember this is my data booklet, so 36,000 divided by 96,500, this is going to give me 0.3731 mole of electrons. Now, Ag plus 1 electron goes to Ag solid. So I can say that the mole of Ag solid produced is going to be equal to the mole of electrons that pass through the cell, which is 0.3731. So the mass of silver is going to be equal to good old N times Mr, which is going to be equal to 0.3731 mole multiplied by the molar mass of silver, 107.9, is going to give me an overall 40.25 grams of silver. And I'm going to look at my significant figures, 3 here, so it's going to be equal to 40.3 grams of silver will be deposited on or plated onto the object at the cathode. Hopefully that made sense, so that now you can pause this video, go have a look at sample question 2 and see how you go. Okay, so hopefully you've had a go at this and you've noticed that this time we're talking about copper. because we're talking about copper, we're going to be looking at a copper 2 plus 2 electrons is going to be my copper solid. Okay, so I've got to keep this in mind when I think about what I'm doing. Okay, so I want to deposit 50 grams of copper. So mass of copper is 50 grams. So first things first, that I've got to work that into a number of moles. So the number of mole of copper is going to be equal to the mass divided by the molar mass. It's going to be 50 divided by 63.5 for copper, which is going to give me 0.787 mole of copper. Okay, because all things come back to stoichiometry, then the amount of copper that I want, N of copper is this, so N of electrons is going to be 2 over 1 times N of copper. Okay, so that means it's going to be 0.787 multiplied by 2, okay, which is equal to 1.57 mole of electrons will be required to deposit 50 grams of copper. If Q is equal to N of electrons times Faraday, okay, then I'm going to have 1.57 mole of electrons multiplied by the charge on 1 mole of electrons, which is a Faraday, which is going to equal to 152,000 coulombs. Okay, so that is the quantity of charge that has to go through my cell. I've been told it's going to be at 8 amps, and I want to work out the time required. So if Q is equal to IT, then I want to find time. Time is going to be Q divided by I. So 152,123 divided by 8.0 amps is going to give me 316.67, it's going to give me 19,000 seconds, and that's a really ridiculous number. So we want to try and get it to 3 significant figures. So 316.67 minutes. And again, we can divide that by 60 again, and we can find that we would need to run this cell for 5.27 hours in order to deposit 50 grams of copper. Okay, there's plenty of questions in your textbooks to practice this. You can see that we can ask it in terms of mass or number of electrons, and we always have to check on the charge on the metal that we're trying to plate. And remember, it's an electrolytic process, non-spontaneous, so we have to force the electrons in, and the cathode must be the object we want to plate. The anode must be the metal that we are hoping to plate with, and the solution is a salt of that metal as well. Remember to gather any questions, take some notes, and have a bit of practice.